Hi everyone. In the last lecture, we have discussed the rotation spectra for the diatomic molecule. In this lecture, we are going to discuss vibration spectra of diatomic molecule. So here, all of you know that when the molecule interact with the IR radiation, that is a 10 raised to 3 to 10 raised to 5 nanometer, then there is a change in the vibrational energy level, and here we get the vibration spectra, or it is also called as the infrared spectra or infrared spectroscopy. So here IR spectroscopy is one of the most powerful analytical techniques which offer the possibility of chemical identification and quantitative analysis. Generally here the IR spectrum, it can be very useful for the identification of the chemical substances. So the technique provide useful information very quickly about the structure of the molecule, and this method can solve the many problems of the organic as well as the coordination chemistry. That means here this IR spectroscopy or the vibration spectroscopy, it is very useful for the organic chemist as well as for the coordination chemistry to solve the various problem related to the molecules. So here after absorption of the IR radiation, that is a 10 to 3 to 10 to 5 nanometer, the molecule chemical substance vibrate at many rates of vibration and giving rise to the close packed absorption bands called as the IR absorption spectrum. So here various bands will be present in IR spectrum. So here when we consider the IR spectrum of any organic molecule, various bands will be present in the IR spectrum, and these bands will correspond to the characteristics, functional group and bond present in the molecule. Thus, here the IR spectrum of the chemical substance is a fingerprint for its identification. That means here we have the IR spectrum of any organic molecule. From the spectrum we can identify that molecule. So here all of you know that the person or the man, he can be identified from his fingerprint. Similar way here, if we have the IR spectrum of the organic molecule or organic compound, then here that compound that can be identified with the help of the IR spectrum. So here IR spectrum of the chemical substance is a fingerprint for its identification. Then vibration motion of the diatomic molecule. So here the diatomic molecule is considered to be simple harmonic oscillator. A bond between the two atoms, it can be considered as the spring. So here the bond between the two atoms, it is considered as a spring, and let us further assume that one end, that is a one atom of the bond is stationary. So here one end of the bond is stationary, that means here the one atom is stationary, considered as a stationary, and the other atom or other end oscillate from the equilibrium position. So let us consider this diagram. So here this is the at rest, this is the first atom, and this is the second atom, and here this is the equilibrium position. So here one atom or one end, it is at stationary, while the second end or the second atom, it can be oscillate from the equilibrium position. So here when the atom oscillate, there is a displacement of the atom from the equilibrium position. So here the restoring force, that is F, acting in the opposite direction to the displacement. Due to the restoring force, the spring is brought back to its original position. So let us consider the second diagram here. That is this is a stretched position of the spring. So here this is a X is the displacement, while here this F is the restoring force, and here the restoring force it act in the opposite direction of the displacement, and because of this restoring force, the spring brought back to its original position. So this is the original position, and because of the restoring force, here the spring it is brought back to its original position. So this is a stretched position, while this is the contracted position. X is the displacement, this is the equilibrium position, and this F, that is the restoring force, it act in the opposite direction of the displacement. That's why again here the spring is brought back to its original position, that is at equilibrium position. So here according to the Hooke's law, the restoring force is proportional to the amount of the displacements of the mass from the equilibrium position. So, here vibration of the spring system. Then here for such oscillator, wave mechanics show that the vibrational energy EV is related to the fundamental vibrational frequency omega bar by the relation. So, here the EV, that is the vibrational energy in joule, it is given by the equation as per wave mechanics, that is a V plus 1 half Hc omega bar. This is the equation number 1, where V is the vibrational quantum number and its values are 0, 1, 2, 3, 4, 5 and so on. So, here in this equation H is the Planck constant and C is the velocity of the light. So, here the omega bar. So, omega bar it is the fundamental vibrational frequency in centimeter inverse. So, here the omega bar is equal to omega by C. So, here what is the omega? Omega is the fundamental vibrational frequency in cycle per second or the hertz, and C is the velocity of the light. So, omega bar is equal to omega by C. From this equation we can find out the omega. So, here the omega is equal to 1 upon 2 pi under root k by mu cycle per second or the hertz. Generally here the omega bar it is expressed in terms of the centimeter inverse, while the omega fundamental vibrational frequency it is expressed in terms of cycle per second or the hertz. So, here the omega is equal to 1 upon 2 pi under root k by mu, where mu is called as the reduced mass of the molecule, while k is called as the force constant, C is the velocity of the light, and here H is the Planck constant. So, here the k, that is the force constant, it is equal to 4 pi square mu omega square. So, with the help of this expression it is possible to calculate the force constant for the particular molecule. So, here then let us consider the next point, the convention regarding equation 1. So, here we have the equation 1, that is a epsilon V in centimeter inverse. So, here E is the vibrational energy in terms of joule. If we have to convert it is into the centimeter inverse. So, here all of you know that we have to divide by the SC. Already we have discussed this point in the rotation spectra. So, here generally here the energy in the joule it is a convert into the energy in centimeter inverse just by dividing SC. So, here V plus 1 half SC omega bar divided by SC. So, here this SC is cancelled, and finally here epsilon V in centimeter inverse is equal to V plus 1 half omega bar. This is the equation number 2. So, here friends, what is important here? V is the vibrational quantum number and its value is 0, 1, 2, 3, 4 and so on. By substituting the value of the V here it is possible to calculate or to find out the allowed vibrational energy level in the centimeter inverse. So, here it is given in the following table just by substituting the value of the V 0, 1, 2, 3, 4, 5 and so on. So, let us substitute the first value V is equal to 0. So, here when we substitute V is equal to 0, 0 plus 1 half, so 1 half omega bar. So, here V is equal to 0, that is 1 half omega bar. Then here the second one is the V is equal to 1. So, here 1 plus 1 half, that is a 3 by 2. So, 3 by 2 omega bar. Then V is equal to 2, the value of the vibrational energy, it is a 5 by 2 omega bar. V is equal to 3, 7 by 2 omega bar. V is equal to 4, 9 by 2 omega bar. Just substitute here instead of V, we have to substitute 4. So, here 9 by 2 omega bar. V is equal to 5, 11 by 2 omega bar. V is equal to 6, 13 by 2 omega bar and so on. So, these are the allowed vibrational energy in centimeter inverse for the difference value of the vibrational quantum number. Then here vibration spectra for the harmonic oscillator model, that is for the diatomic molecule. So, here epsilon V is equal to EV divided by SC, that is the V plus 1 half omega bar centimeter inverse, already we have discussed it. So, here V is equal to 0. So, here when we substitute the V is equal to 0, so 1 half omega bar, so centimeter inverse. So, this epsilon 0 is equal to 1 half omega bar centimeter inverse, it is called as the 0 point energy, and here the implication is that the diatomic molecule can never have the 0 vibrational energy. The atoms can never be completely at rest relatively to each other. So, here when we substitute the V is equal to 0, this epsilon 0, it is not equal to 0, but it is equal to 1/2 omega bar, and this energy it is called as the 0 point energy. And from this equation here we can conclude that is the atoms can never be completely at rest relative to each other. Then here let us consider the selection rule for the vibration spectra or for the IR spectra for the diatomic molecule. So, here the selection rule is delta V is equal to plus minus 1. So, here the allowed vibrational energy level. So, these are the allowed vibrational energy level. So, here when the V is equal to 0, so it is a 1/2 omega bar, then V is equal to 1, it is a 3/2 omega bar, V is equal to 2, 5/2 omega bar, so on. So, 7/2 omega bar, 9/2 omega bar, 11/2 omega bar. So, these are the allowed vibrational energy level. Then the transition between them for a diatomic molecule. So, here the selection rule is delta V is equal to plus minus 1. So, here all of you know that when we consider the delta V is equal to plus 1, we get the absorption spectra, and delta V is equal to minus 1, we get the emission spectra. So, let us consider here the absorption spectrum. So, this is the first transition, V is equal to 0 to V is equal to 1. Then here V is equal to 1 to V is equal to 2, this is the second transition. Then third transition, V is equal to 2 to V is equal to 3, this is the third transition, because the selection rule is delta V is equal to plus 1. So, these are the allowed transition. So, here these are the allowed transition. This is the first transition, this is the second transition, this is the third transition, then this is the fourth transition as per the selection rule, and while this is the vibration spectra or this is the IR spectra for the diatomic molecule. Then here it is a seen from the table and the diagram that for V is equal to 0. So, here the value of the vibration energy, it is a 1/2 omega bar centimeter inverse for the diatomic molecule. So, here vibration energy can never have 0 value, the atom can never be completely at rest relatively to each other. So, here this quantity 1/2 omega bar centimeter inverse or here 1/2 SC omega bar joule is known as 0 point energy. And here the 0 point energy, it depends on the strength of the chemical bond and the atomic masses. So, here selection rule, all of you know that delta V is equal to plus minus 1. So, here when the IR radiation interact with the molecule, energy is absorbed and the molecule is raised to the higher vibrational energy level by 1 unit. Thus, the occur change in the dipole moment of the molecule and one get the vibration spectra. Again here the molecule which has the permanent dipole moment, only those molecules they are the IR active or they give the vibration spectra. It means vibration spectra is observed only in case of the heteronuclear molecule with the dipole moment has finite value and not in case of the homonuclear molecule where the dipole moment is 0. Thus, the molecule said to be IR active and IR inactive depending upon the dipole moment value. So, here only the polar molecule they give the IR spectra or they give the vibration spectra, non-polar molecule they does not give the IR or the vibration spectra. So, applying the selection rule and referring the equation number 2 we have. So, here this is epsilon V in centimeter inverse. So, this is a 0 point energy V plus 1/2 omega bar, this is the equation number 2. So, here delta epsilon in centimeter inverse absorbed energy. So, let us consider the general transition, that is a V2 V plus 1. So, here the absorbed energy, it is the epsilon V plus 1 minus epsilon V. So, here the V plus 1 plus 1/2. So, instead of V substitute the V plus 1. So, here the V plus 1 plus 1/2 omega bar and here the V plus 1/2, because here we have considered the general transition, that is a V2 V plus 1. So, here plus V and the minus V it will be cancelled. So, 1 plus 1/2 that is a 3/2. So, 3/2 omega bar minus 1/2 omega bar, it is a omega bar. So, this is the general transition. Then here when we consider the transition from 0 to 1, again here the energy absorbed it is a omega bar, that is a 3/2 minus 1/2. Then here when we consider the next transition, so let us consider the diagram once again. So, here 0 to 1, so energy absorbed it is omega bar. Then here when we consider the transition 1 to 2, so here it is a 5/2 minus 3/2, again the answer is the omega bar. Then let us consider the next transition, that is the 2 to 3. So, here the 7/2 minus 5/2, again the energy absorbed, it is omega bar. That means here when we consider the vibration spectra or the IR spectra for the diatomic molecule, so here all the line falls at the same place, that is the omega bar centimeter inverse. So here for the general transition, that is the V to V plus 1, that is the omega bar centimeter inverse. So here the corresponding absorption line will occur at the fundamental vibrational frequency omega bar centimeter inverse position in the spectrum, and this can be represented as, that is a nu bar from V to V plus 1, that is it is equal to omega bar centimeter inverse. So friends, here when we consider the pure vibration spectra or the pure IR spectra for the diatomic molecule, so here when we consider all the transition, that is V is equal to 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. So all the lines falls at the same place, that is a omega bar centimeter inverse. So friends, in today's lecture or in this lecture we have discussed the vibration spectra for the diatomic molecule. Thank you.